Welcome back everyone to the second part of my guide to the Tricksy Foxes mod. Today, we're going to be starting to learn about the behavior tree system and its editor. This is going to be a big one. Once you have access to the inventory screen of a Tricksy mob by apprenticing it, click on the tree post-it note to access their behavior tree in the editor. Behavior trees are made of component parts called nodes, which usually have a preceding parent node and may have one or more child nodes. In the editor, we can click on a given node to focus and modify it. The first node in the tree is typically called the root node. The number of nodes in a mob's tree can vary significantly, but it's limited to 25 nodes by default. This limit can be changed in the server config and is ignored for players in creative mode. Nodes can be given custom names, and their descendant nodes can be hidden to aid the player in understanding what a given branch does. Each in-game tick, of which there are typically about 20 per second, a Tricksy mob sends pulses to its root node, which then passes them down the train through the rest of the tree. In response to a pulse, a node returns one of three distinct results: failure, success, or running. If a mob's root node reports a failure result, there is a short delay before they next pulse their tree. Some types of node also have a cooldown to limit how frequently they can be used by any one mob, chiefly as a lag reduction measure. There are four major types of node: control flow, decorator, condition, and leaf nodes. Control flow nodes, as their name implies, control how pulses travel from them to their child nodes. Selector nodes will send pulses to the first child that doesn't return a failure result, and will continue doing so until it returns failure or success. Selectors are therefore good for building responsive behaviors, like finding a tool before attempting to mine. Sequence nodes will send pulses to each child in order until either the last child returns success, or any child returns failure. Most forms of automation are invariably made from one or more sequences, but these are often quite inflexible. Reactive nodes will send pulses to all child nodes at once until any child returns failure, or all of them have returned success. This is useful for multitasking. Decorator nodes modify the result of their child node, allowing us to modify the logic of a given branch. The most common decorator is the inverter, which returns failure if the child node returns success, and vice versa. A repeat node will continue to send pulses to its child node until it fails or has succeeded a certain number of times. In contrast, a retry node will pulse its child node until it returns success or it's run out of attempts. Do once nodes, as the name suggests, only send a pulse to the child node until it returns either failure or success, and then never runs again until the mob is loaded from memory. This is useful for setup behaviors like checking equipment. Lastly, the force failure and force success nodes return only their respective result as long as the child node does not return running. This is useful for when a behavior needs to be run, but the outcome doesn't actually matter all that much. Condition nodes evaluate something, usually the mob, surroundings, or whiteboards, and immediately returns either failure or success. There is a large variety of condition nodes, allowing for a wide range of information to be evaluated. For further information, check the wiki. For further variety, they are often combined with decorator nodes like the inverter. Last but certainly not least, leaf nodes never have child nodes and are used to effect an actual change to the mob, its whiteboard, or the environment. Similar to conditions, there are a great many types of leaf node. Additionally, each Tricksy mob has access to one or more special leaf nodes, which are unique to that type of mob. Tricksy Foxes can revert to their quadrupedal posture and back, allowing them to pass through single-block tall passages, place temporary foxfire lights, and pray at prescient candles to change the comparator output of all candles bound to the same mob. Tricksy Goats can leap tall bounds, charge through enemies, and strike a sturdy pose to block hallways. Tricksy Wolves can leash or unleash animals, bless allies to heal them or harm undead, and howl to alert other Tricksy Wolves to their position. This is certainly not an exhaustive list of all of the different types of node available in the mod. See the wiki for a complete description of each. In order to store information long term, Tricksy mobs have access to persistent data storage objects named whiteboards. Principally, they can use their own personal whiteboard, a sage whiteboard tied to their sage and shared by all apprentices of that same sage, and a constants whiteboard containing common useful values like the 6 cardinal directions. All whiteboards come with pre-existing values that are calculated and updated automatically, but you can add your own to the mob's whiteboard by the whiteboard screen. The values in all whiteboards, except for the personal whiteboard, cannot be altered by the behavior tree. However, the values within those whiteboards can be copied into the personal whiteboard using the copy value leaf node and altered from there. Whilst you can store all manner of information in a whiteboard, nodes will also accept static values. These are unchangeable and not accessible by other nodes, making configuration of individual nodes much easier. Values inside of whiteboards each have a specific type, such as a position, entity, number, or item. In many cases, these types can be used in contexts where they don't match exactly, such as using an entity as a position value. Values can also store lists of the same type of value, such as a set of positions for a patrol route, or a group of entities representing livestock to feed. List values can be sorted and cycled through using appropriate leaf nodes from the Whiteboard tab. As a basic example, let's review the initial behavior tree used by freshly apprenticed Tricksy mobs. This tree intentionally contains some flaws. Can you spot them before I point them out? The root of this tree is a selector. In most cases, the root node is either a selector or a sequence. Because this tree has multiple distinct behaviors instead of a rigid sequence of actions, it uses the selector to choose the most appropriate one to enact. The first behavior is its startup, where we use a do-once-decorator node to ensure that we only run it when the tree is first pulsed when the mob spawns or is loaded. This behavior then uses the setHome-leaf node to store the mob's current position. This is then used by the next behavior to ensure they don't wander too far afield. The meander behavior is the next that the selector will evaluate. As a sequence node, it runs its child nodes one by one in order. First, it checks the values equal condition to see if it does not have a sage. It is a common practice to put conditions at the top of sequences or in reactive nodes this way to ensure the sequence can complete before starting it. Once we have verified that the mob does not currently have a sage, we make them issue a bark. This emits a sound and temporarily displays an icon above the mob's head and can be accessed by the getBarkLeaf node. In game design, bark refers to a sound effect and animation used to convey an intended reasoning to the player, such as to highlight that they have found an enemy or completed a task. Here, we just want the mob to look panicked. Next, we use the Force Success decorator on a Wanderleaf node. The Wander node will return failure if it cannot find anywhere to move to around the mob's home position, so the decorator prevents it from interrupting the rest of the sequence. Lastly, in this behavior, we have the mob look around, as though hoping to find guidance from a sage. The third and final behavior in this tree is to follow the mob's sage. Since we've already passed over a behavior that first checks if the mob doesn't have a sage, we know at this position that they do, or else the selector wouldn't reach here. So we don't need to check that condition again. Similar to the meander behavior, we check a condition to see if the nearest sage is closer than 4 blocks away. Then invert it so the rest of the sequence only runs when they are further than that. If we pass that condition, we then use the sage entity as a position value and have the mob walk over to them. A useful tool when reviewing behavior trees is the prescient candle. As mentioned in the last episode, we can see the pulses passing through a mob's behavior tree by right-clicking on any candle tied to them. This can help us to identify exactly where things might be going awry whilst designing a behavior, as well as indicate where the tree might be spending more time than necessary. Did you spot the flaws in this behavior tree? If you spotted that the meander sequence will bark every few ticks if the wander node fails instead of barking in between movements, congratulations! You now know how to make a noise machine from a fox. This flaw could be resolved by putting the wander node in a selector with a wait node at the end to ensure a minimum span of time between screams. If you also spotted that the fox will set their home position every single time they are loaded into the world, you get a gold star. This means they may ultimately wander afield further than intended and could be resolved with a check for whether their home position has already been set using the value exists condition aimed at the home value before running setHome. Well, that's all for today. In the next episode, we'll learn more about using the editor and put our knowledge into practice designing some simple behaviors. See you then.